Hello, and welcome again to Machine Learning Tips. So today we are going to be looking at lab one for regression, where we are going to be using a popular data set called the wine quality data set, which we can see this data set from the UCI Machine Learning Repository. Did mention how you can do that, and that will be the data we'll be using. Also, I will be posting the link to this data set in the comment section so that if you want to practice, you can keep practicing. So the first thing we are going to do is import libraries and then load that data. We will do some exploratory data analysis. We are going to split the data into training, validation, and test set. We will do some future scaling, model training, evaluate our model, and also look at the model coefficient to see which is the top future that is, contribute the most in predicting what the wine quality. So the first thing we are going to be importing these libraries that we are going to be using. One thing you have to know here is that for these other libraries, we have seen them more. The library we'll be using more for machine learning is what the this scikit-learn library, where we are going to import from scikit. We want to import model selection, where we import the train test, which will enable us to what to split that data into training, the test, and what and the testing data. Also, we will be using from scikit-learn. We will dot what linear model. We are going to import what linear regression, which is what the model we are going to be training, and then from scikit-learn.metrics, what we are going to be using to evaluate our model, we're going to import what the mean squared error, the mean absolute error. The mean absolute error here is close, same as the similar to the mean squared error, but here we are going to be looking at the absolute difference between what they predicted and what the observed value. So first thing is just to go and copy the URL from that UCI machinery for this data set. And then since it's a CSV file, we'll do pd.read underscore CSV, we'll pass that URL. Then we are passing this SEP here because that data is separated with what columns. And then we do that, we can run this just to see. Shape here is going to give us what? The number of rows and what? The number of columns in that data. So we can see here we have like 1,559 rows and what? And the 12 columns. So the 12 columns, the target variable here will be using these other 11 features to predict what? To predict the quality of wine. So also we want to just check the data set to see whether we have any categorical attributes or features in that data set. We can see that all of them we are float and what integers, which means that they are what we are numeric. And so another thing we want to do is, I did mention of the correlation. We are building a regression model, so most of the times we want to see how correlated is what is the target variable with those input features. Sometimes with real world applications, we might not really find that linear correlation between the target and the features, but linear regression is just a baseline to start with, because when we come to non-linear models, most of those models are very, very applicable in real world applications or real world problems, because they real world problems, the data doesn't really have that linear relationship between the target and those features. So here we can see these diagonals are just ones, because it is like we are looking at the correlation between a feature and itself. We can see here that sulfur here is giving us 1. One thing we should note here is that if we look at the correlation between wine quality and alcohol, we can see here that this has the highest correlation, which is what? 0.48. The other ones are pretty very low. The other ones are pretty very low. And another second one here is what? Volatile acidity, which also has the second correlation. The other ones are pretty very low. This one, the correlation between wine quality and PHP is like minus 0.06. But guys, this is just to show you how we can look at that correlation between the target variable and the input features. One thing I did mention about the multiple collinearity. Most of the times we don't want high correlation coefficient between these input features. We can see here that fixed acidity has a very high correlation with what? PHP. So most of the times, if we are going to use this model, this high correlation, we might decide to drop one of these features to see whether the model is going to improve or not as we go on. But we are going to do that more maybe in the next labs. Today, we just want to start with some baseline and see how we can fit a model with some real-world data set. So we want to look at the distribution of the target variable just to see. We can see here that that wine quality is categorized into what? We have quality of 3, 4, 5, 6, 7, and 8. But we can see here that 5 has the highest distribution, that's the highest count. We can also look at the futures, that the scatter plot between what futures and what the target. Most of the times, if this target variable was actually a continuous future, or maybe continuous, and then we should have been having this to be, this distribution between the futures to be having something like, some histogram shape, or what we call the normal distribution, which will be having something like this. But because the target is just made up of integers, when we plot the scatter plot between that target and the futures, we'll be having something like the distribution will be looking more like what? Like count. You see? So, yeah. And after that, we decided to like cut that data. So the first thing, because I want to look at the first of all, grab those futures. Futures here are the input futures, and then we have the target. So we want to drop the wine quality from that data frame, because so that the other futures will now just be 11. And then now I want to extract that target variable, which is wine quality. We have seen how to extract this. So when I do this, I need to cut that data into train, test, split, so that I will have the training, the validation, and the test set. This will enable us look at how our model is performing. So the train set will be used to evaluate those different model parameters or model coefficients. And then we can use the validation to see how the model is performing. And then the test set is just like seeing how that model perform with data that it wasn't seen during training, like some real world application. So when we run this, we are going to see the different proportions of the train, the validation, and the test set. We can see that the validation set and the test set here are same, and the number of columns here are just 11, because we are not considering the target variable as an input to that linear regression. So after that, we are doing future scaling here, which is a good practice, because most of the times, as I did mention, that linear regression is being affected by a lot of outliers. So we do this to solve that problem, so that that data, can be within a particular scale. When we do this, then we can call this, next thing is to train our model. So we are calling area to be the linear regression, because we already imported this linear regression when we were importing our libraries here. So we are going to call that, and then when we call it, we will fit. So fitting here is just the process of what? Estimating those model coefficients. So I will fit a model by passing what? The train test, where the training data, which I scaled it, as well as what the target variable, because it's like we are mapping some input to the target. That's why we are during the fitting process, we have the input and that target. If I run this, we already have our model trained, because it's pretty fast, because the data is not much. And then we have to evaluate our model. We will evaluate the model using the root mean squared error, which is like the square root of the mean squared error. And then we are going to use the mean absolute error, which is like the absolute difference between the predicted value and the observed value. Remember, the mean squared error, we saw the formula, which is like the square difference between what? The predicted value and the observed. So we are looking at the mean of that square difference. So and then here we want to return that predicted value, which is this, and then now we can look at the model performance. So we will call this function here, and then we'll evaluate that function with the different that's the train, the validation, and the test set. So we call that function. We pass in that model we trained. We have what? We pass in the scaled input and the target. The same with the validation. We pass the model, we pass in the validation input and what the target. The same with what the test set. If we run this, we are going to see the model performance. So for the test set, we have the mean squared error for the test set, which is like approximately 0.42. The root mean squared error, which is the square root of this mean squared error, which is approximately 0.65. For the mean absolute error, we have it is approximately 0.5. So if we look at the mean squared error for the validation and the mean squared error for what the training, these values are pretty close. There is not much difference between them. Same, one thing we have to note here is that the model has to, be much more, perform much better with data that it hasn't seen. So we can see here that the test set mean squared error is pretty lower than that for what the train and the validation, which is actually what we want. We want that, if this model is deployed to any real world application, we should be having a better performance with data that the model didn't see during training. Same, we can see that the mean squared error here for this is still is pretty lower. Then with the mean absolute error for the training, the validation and the test set, they are pretty same, which that is what we are looking for. So here, most of the times when we have this not having much discrepancy in between these different evaluation methods, between the training, the test, and the validation, then we can say pretty well that that model is performing well. It is not overfitting. If it was overfitting, we might have a very low mean squared error for the training, and then very high values for the train, for the validation and the test set. So because the values are pretty lower here especially for the test set, then we can say that model is doing well with data that it didn't see during the training process. That is when it was estimating those model coefficients or those model parameters. Also, I looked at the model coefficient. This enabled us to see which of these features actually contributed most in predicting that wine quality. We can see here that the first feature here is alcohol. The model coefficient here is approximately like 0.27, like 27%. And if we go back to this correlation heat map, we can see here that alcohol had a very high correlation with wine quality. Also, if we go back to the model coefficient, we can see that sulfur is the next one, which is like approximately 14%. If we also go back to the correlation heat map, let's go to sulfur and see that the correlation coefficient between between wine quality and sulfur was at around 0.25, which that is why we see that those features tend to be the top features in contributing to the prediction of wine quality. Guys, that was it for today. We will keep looking at more of these labs so that we can grab most of the concepts on how most of these models they work in real world applications. One thing you have to know here is that we are starting from linear regression because it is very easy to interpret. When we go to non-linear models, sometimes it is difficult to actually see whether when there is a change in alcohol, how does that change affect the wine quality? You cannot really see that linear relationship for most of these non-linear models. So guys, keep following for more. You can follow me on Facebook and also subscribe to my YouTube channel for more of these tips. Thank you so much.